Maybe I could start with a few words on the topic. So my presentation today is focusing safe and sustainable by design chemicals and materials. And I will mainly focus, as already heard, on chemoinformatics contributions towards this direction. So I will first give you a short overview of the safe and sustainable by design concept and how this fits within the European Union Green Deal and the chemical strategy for sustainability. And then I will make, let's say, a deeper focus on the chemoinformatics contributions. And I will also briefly show you two case studies related from, actually taken from the nanosafety field related to the safer by design chemicals. So yes, that's the one. So if we move on to the next slide, which contains the contents, okay. And then maybe the next one also, because first of all, I would like to highlight the European Green Deal. And with the European Green Deal, the Commission actually aspires to become the first climate neutral continent by 2050. The Green Deal defines four interlinked policy goals, which will drive the transition to a sustainable economy and society. And these include climate neutrality, biodiversity protection, circular economy, and the zero pollution ambition for a toxic-free environment. And then for the next slide, please, to achieve these goals that I have just mentioned, several strategies and action plans were adopted, among which the chemical strategy for sustainability, which actually aims to tackle the challenge of producing and using chemicals to address societal needs, whilst of course respecting the planetary boundaries and avoiding harm to humans and the environment. And the EU chemical strategy for sustainability actually aims at fostering a transition towards safer and more sustainable chemicals. And to ensure this transition, safety and sustainability considerations should be integrated when assessing existing chemicals or when alternative chemicals are used that might substitute the first ones. So the operationalization actually of the safe and sustainable by design concept is one of the ambition of the chemical strategy. And the next slide, please. So furthermore, European Union, European Commission's actually strategic research and innovation plan aims to accelerate the transition to safe and sustainable chemicals and materials. And the plan, as part of the chemical strategy for sustainability, highlights crucial research and innovation needs. And for this shift across the full, let's say, life cycle of chemicals from design to their end of life. This strategic research and innovation plan highlights the research and innovation areas crucial for making chemicals and materials safe and sustainable, and supports the safe and sustainable by design framework. This is a framework that sets out an approach to assess the safety and sustainability of chemical or materials across their life cycle. And this plan will support the safe and sustainable by design framework through, for example, innovative methods and models, better data availability for the assessment and innovation for the transition to safer and more sustainable production processes and end-of-life options. So for the next slide, we see the United Nations Sustainable Development Goals, and given that chemicals and materials affect almost all aspects of development, the safe, the strategic research and innovation plan will support several of these goals, as seen on the slide. In particular, it can support goal number 12 on sustainable consumption and production, but beyond that, also goal on food security. This is goal number 2, health, goal number 3, and sustainable cities, goal number 11. And also enabling safe and sustainable production processes and technologies may help to achieve goal number 9 on industry innovation and infrastructure. And the next slide, please, where we again highlight the European Union chemical strategy for sustainability that plans to foresee, the action plan actually foresees the development of a framework to define safe and sustainable by design criteria for chemicals and materials. And this safe and sustainable by design approach is very important to support the design, the development, the production, the use of chemicals and materials that focus on providing a desirable function or service while avoiding or minimizing, let's say, harmful impacts to human health and the environment. These all have been already highlighted in a JRC, a very recent JRC technical report on safe and sustainable by design chemicals and materials. So for the next slide, please, if we go to chemoinformatics contribution, how can chemoinformatics underpin these efforts? This is the next slide, please. Or I don't see it changing. I'm not sure. We need to go a slide afterwards. Can you hear me? Can you change the slide or?
Who is dealing with the slides of Professor?
Okay, thank you very much. Yes, that's the one. So chemoinformatics is, let's give a definition first. Chemoinformatics is a multidisciplinary field of research combining chemistry, biology, physics, mathematics, and informatics, and provides in silico methods and tools to facilitate material design and optimization and support decision making. So among the different in silico tools already offered, already available, I can name a few like predictive modeling, machine learning and artificial intelligence, data-driven models actually, and then molecular modeling and simulation, molecular docking, data mining, virtual screening, and de novo design. Next slide, please. So as we now have an extended production and use of new advanced material, this actually increases the risk of environmental release and undesirable environmental and biological effects. And so computational in silico approaches have been proposed to support and sometimes maybe substitute wet lab experiments to assist with risk assessment as well as safe by design strategies for the design, for the improvement and the production of safer material. So we can see on the right hand of the slide, let's say the life cycle of such models, such tools that can underpin the whole effort of designing safer chemicals or materials. And if we go to the next slide, so we have the development of materials informatics innovation pipeline. This combined design of experiment approaches, physics-based materials modeling, data-driven machine learning modeling, including multi-criteria optimization, and of course, the ultimate goal, let's say, of the inverse design of advanced materials as foreseen to support the safe and sustainable by design concept. And then this pipeline can be designed to support decisions. So we need the decision support tools for different stakeholders, for the industry, for regulators, for other authorities or the academia in the assessment of chemicals and materials functionality, safety, and sustainability. And next slide, please. If we focus particularly in a data-driven model, then we have overall a computational workflow that includes 3 main steps. The first one, of course, is the data collection that the data could be either generated or collected, but they need to be organized, they need to be curated. We need data to be fair, as we say. Fair stands for findable, accessible, interoperable, and reusable. And then we need to exploit this data in a data-driven, let's say, context through machine learning and artificial intelligence. And then, so we build predictive models, and then we, based on these models, we make tools available for any interested party to use, tools that will be available as web services or as standalone applications. So these are the three main steps for data-driven model development. And if we go to the next slide, please. So just a few examples to highlight. For example, a recent demonstration that has been recently also published has to do with assessing the cytotoxicity of different metal oxide nanoparticles. The data were collected from a recent publication of 2012. And actually, they were retrieved from the S-Square Nano database. And this data had to do with the cytotoxicity of the metal oxide nanoparticles in two different cell lines. We had originally data for the physicochemical characteristic properties of the nanoparticles, the molecular properties of the nanoparticles, and also some AC-related descriptors. And these were enriched with more computationally derived atomistic descriptors. So in total, there was almost 500 data points. And this data set was imported, was verified actually, and was imported to a Nanopharos database, including European Registry of Materials identifiers. If we go to the next slide, we will see, I think, yes, a screenshot of the Nanopharos data set where all these data are included. This is a very important step, the curation, the organization of data for the full set of metal oxide nanoparticles and their characteristics and properties. And then if we go to the next slide, we will see the significant descriptors that were highlighted. These include the physicochemical descriptors, molecular atomistic descriptors, or, as I said, the AC-related descriptors. This is something unique for its case when you need to exploit a specific data set. So next slide, we will see the actual, let's say, chemical space of the data set, where we need to identify the different neighbors of its data, of its, let's say, metal oxide, and then based on the response on the activity, on the toxicity, in this case, of the neighbors, we can predict, we can assess the toxicity of a given metal oxide of our interest. And this tool, as we see in the next slide, please, can be made available as a web service, so that actually the goal is that its model developed does not remain within the closed group of the developer, but it's also disseminated as a web service or as a standalone application for anyone interested to use. And this is the interface, a user-friendly interface for the specific service to be used for next predictions, let's say. And in the next slide, I will close with another example. I will be very brief also on that. It's a, let's say, safe by design paradigm for the design of functionalized carbon nanotubes. So we see we have a set of different small molecules, let's say, that are decorating carbon nanotubes, and we have we had 83 such different carbon nanotubes, and we have calculated almost 800 descriptors per carbon nanotubes, accounting for the topological, geometric, structural characteristic of these organic modifiers. And if we go into the next slide, we will see the actual data as included again and verified within the Nanopharos database. And then if we go to the next slide, we will see the different steps used to develop the predictive model. We see the total number of data used, 23 diverse compounds, almost 800, as I said, descriptors per carbon nanotube, decorated with the organic molecule, of course, and steps that we have taken based on data-driven, again, modeling context to derive a predictive model at the end. It's very important that for each case, we define the limitations of the model. So we define the domain of applicability of the model to see whether we can produce reliable predictions for any given new compound of our interest. So we go to the next slide, I think. Yes, we have the workflow, let's say. We have the workflow that identifies the closest neighbors, as we said in the previous example also. And based on these neighbors, we predict the behavior of a novel structure. And I think I have another slide on this one, if we go to the next one. Yes, this is again the interface, the user-friendly interface for the model to be made available, where one can also sketch, can use a chemical sketcher, as you can see on the screen, to sketch a different compound or change substituents in different positions. And then in this way, virtually experiment with the different compounds and see how the activity, the toxicity, the response is changing based on the structural changing that someone is introducing to the lead compound. So I think we can go to the next slide now. Yes, some highlights to sum up, to wrap up. We have advanced materials, as we said, as critical drivers of innovation across a range of important technologies and industrial sectors. Of course, underpinning key areas of high-value manufacturing, areas such as healthcare, electronics, energy, and many more. And we have chemoinformatics as a multidisciplinary field of research that help us screen millions or more possible candidate compounds computationally for a given application or for a set of properties. And this, of course, is resulting in new leads for experimentalists, as a great number of parameters can be computationally screened and explored. And in this way, we open up to previously, let's say, unconsidered avenues of research. And one of the most important features of machine learning assisted methods is the ability to predict or stimulate, let's say, a wide range of materials and chemical properties prior to their development, their synthesis, and their application. So advanced, to conclude and summarize, advanced in silico-based design and analysis tools are making now their way into the mainstream of material science and engineering, and the specific capabilities of selecting materials can be used to optimize the design of materials themselves as part of let's say, move forwards a safe and sustainable by design and circular economy, in line, of course, of what we have highlighted from the first slide, in line with the goals of Green Deal and the chemical strategy for sustainability of the EU. So that was, I think, my presentation. Thank you very much for listening and attending. And of course, I will stay for any questions. And I had included also my email in the last slide for anyone who wishes to catch up at a later stage.
Thank you very much, Georgia. And we also thank Efthymis. Efthymi, was it you that helped us with the slides?
Thank you so much, and apologies.
So we have some time, actually 8 minutes till the break, the 2:30 break. I see here a couple of questions. One for Vasilis Chronopoulos. It is a question from Anthony Kalokerinos. In simple words, is it possible to achieve poverty alleviation?
Well, that question is not so simple. That's why the words are not simple. The reality is that if we want, if work integration social enterprises want to contribute to poverty alleviation, they are going to do this by offering good job positions. So what are the good job positions? Those that are well paid and that are close to the concept of full-time. The analysis showed that social enterprises, we're talking about work integration social enterprises, KISPE and KINSEP indexes, are able to develop good job positions that are well paid. Those work integration social enterprises that focus on the open market, that develop entrepreneurial activities focused on the open market, seem to be doing better in developing good jobs. I hope I helped you with that.
Yes, yes, it was very clear, the answer. The problem is if they want to make new jobs, they are able, but do they want?
They do want. It's a matter of existence. The reason that work integration social enterprises are developed is in order for them to develop jobs for people from vulnerable groups by default, by definition. Okay? The reality is that through the years, they focused in the public sector, having procurements with the public sector, which is not bad, but the reality is that the money that those jobs that are supported from public procurements offer to the beneficiaries are not enough. They are not. It's very easy to measure it. They are not over 5,000 euros per year, so they are not enough to keep those people from vulnerable groups that derive from vulnerable groups above the poverty line, because the poverty line in Europe is very well defined in the European Union. So we don't need more jobs. We need good jobs, well-paid jobs, and jobs that are close to the concept of full-time job.
And then we have the fertility gap.
Sorry, come again?
Then we have the fertility gap. People don't have money, they don't get married, and they don't have children. Thank you very much.
Thank you. Thank you too.
Could you please define what do you mean good job, full-time job? Because in Finland, we have 4 days of work per week. In the rest of Europe, we have 7 days of work per week. That means 40 working hours. So could you please define what we talk about?
Of course. Thank you for the question. As I said to the presentation, jobs that are well paid are those that are able, at least to the concept of our research, are those that are the money that they pay to the beneficiary, or let's say to the worker, is enough to keep that person above the poverty line. The poverty line in Greece is about 5,000 euros a year. That's the one. The second, that has to do with how many hours do they work in a year. According to the European Union, that has to do with the 20% of a full-time job, let's say. So a full-time job in Greece is 8 hours a day for 5 days a week. So 20% of that is about 422 hours, working hours per year, because it is a reality in work integration social enterprises, both in Greece and other parts of the world, that they have a lot of beneficiaries, quote, workers, that they could work for 5 hours a month, 6 hours a month. He's a worker, okay? He's a beneficiary. He does have a job, but that job is not close to the concept of full-time. Okay, thank you.
We have one more question another question for Professor Melagraki. It's again from Professor Kalokerinos. The concept is to design safe chemicals and materials, but what about investigation if they can be produced and applied?
Yes, actually, this is a great point, and since I have worked a lot also in the drug discovery projects, this is a main, let's say, question that is of our great interest. Let's say, the synthetic accessibility of the compounds proposed, because I might find a structure that could be non-toxic and with high activity, but when I propose this structure to an organic chemist, for example, this is not something that could be synthesized or it can be accessible via some vendor, or it could take a lot of time and a lot of effort and a lot of money to make it. So we need to take this into account, and this is a problem that we're facing specifically when we're working with the inverse problem. As we said, the inverse problem is that we have a specific activity range of interest, and we need to see which structure fits this activity range. And this is something that we take into account, the synthetic accessibility of compounds proposed, because we can propose anything, but it might be useless if it can be obtained at the end or used.
If I can add to what you just said, cheminformatics is already used in organic synthesis. So they found out how the molecule should look like, and then they try to synthesize it. But
yes, that's true.
Difficulty. The main advantage of cheminformatics is the nano oxides, as you said, and the new materials. Maybe this is the future. Thank you.
Yes, that's true. And there are great, let's say, advances and efforts towards this direction for nanoinformatics, as we call it, specifically for nanomaterials.
Yes, thank you very much.
Thank you.